Alright guys, hope everybody's doing okay. What we're going to do today is look at a short presentation on something called half-life. So where we left off, talking about radioactivity, we looked at elements after 83, and we said that there's really no amount of glue or neutrons that can hold them together permanently. So there are no stable isotopes that exist for elements 84 through the end, through 118. So how do we measure this radioactivity, or what's it look like when the elements break apart? We can measure it with something called a half-life. How long does it take for half of what you have to go away? So I have a short 5-minute video clip to start things out here, which will give us a good understanding and some basic knowledge of half-life. And then we'll go through and fill out a little bit of the information in your packet and do a couple simple calculations. Okay? So let's check this out. Hopefully the audio is good enough and okay, and then we'll pick up after the video. Alright, here we go.
These aren't the only atoms hiding from view. Scientists now know that most elements come in more than one version. The different versions are called isotopes. Consider carbon, the backbone of life. It has 3 natural isotopes, or versions. Each has 6 protons and 6 electrons. That's what makes them all carbon. The difference between them is the number of neutrons in the nucleus. Neutrons are electrically neutral particles that act as glue to hold atoms together. What we think of as normal carbon is called carbon-12, 6 protons plus 6 neutrons. But about 1% of carbon atoms have an extra neutron, giving them 7. They're called carbon-13. And about 1 in a million have 8 neutrons. That's carbon-14. And that rare version of carbon has proven to be a crucial tool for unlocking the past. Several times a year, scientist Scott Stein travels to the shores of Mono Lake near Yosemite National Park. This then is Mono Lake.
Mono Lake, yeah, right here at the foot of the Sierra Nevada.
He's studying the long history of droughts in California, trying to determine how frequently they occur and how long they last. Over the millennia, the water level has risen and fallen as the area has cycled between wet periods and dry times.
So that sandy area should be the level?
During times when climate was dry, Mono Lake dropped down, exposed the shorelands, and allowed trees and shrubs to grow.
When the dry periods ended and the water level rose, the trees drowned, marking the end of the droughts. Since then, the remains of those trees have been well preserved by the arid climate.
These droughts were long persistent.
To determine how long ago these droughts occurred, Scott is using carbon-14 to date the trees. Unlike the other natural isotopes of carbon, carbon-14 is unstable. Over time, its atoms begin to deteriorate. One of its neutrons turns into a proton and spits out an electron. Now with 7 protons instead of 6, it's turned into nitrogen. That process is called radioactive decay, and scientists know exactly how long it will take for half of any amount of carbon-14 to decay away. Scientists call that time its half-life. Living things constantly replenish the carbon in their bodies. Animals from food, plants from the atmosphere. But after death, that process stops. The amount of carbon-12 stays the same, but the carbon-14 decays away at a constant rate, making carbon-14 a ticking atomic clock. To know how long ago this ancient tree died, we just need to count the carbon atoms in a small sample. Piece of cake, if you're this guy.
No, these are fragments of the tree stumps at Mono Lake, and I understand that you are the master of carbon dating.
Physicist Tom Brown works in the carbon dating program at Lawrence Livermore National Laboratory.
In fact, if I'm not mistaken, carbon dating actually pre-existed before internet dating.
Very much.
Carbon-14 can be used to date samples up to 40,000 years old. It's been used to find the ages of many Egyptian mummies and other ancient artifacts.
So how does wood fare
with carbon dating?
Intact wood is very good material to date. It retains the carbon from when that material died, and we're able to extract it, purify it, and get a really good material for dating.
Tom needs only a small amount of wood. Even this tiny sample is overkill. A lab technician cleans it and reduces it to a fine powder.
Oh man, this huge thing? This is your carbon dater-matic 3000?
The actual counting of the atoms takes place here, in the carbon dating accelerator.
I see you bought the camping version.
We have our 1 milligram of carbon from the wood chip sample basically in that hole.
In that tiny little hole?
That's where the 1 milligram of carbon is from that sample.
Not a lot of wood chips.
And we put about 64 of these holders in one of these wheels.
The accelerator applies a powerful electric charge to the atoms, basically lightning, giving them the speed and energy they need to hit a detector with enough force to be counted.
The ratio of the carbon-14 ions to the amount of carbon-12 in the sample tells us how old the sample is.
The fewer the carbon-14s, the older it is?
Yes.
With his accelerator, Tom calculates that our tree died about 150 years ago. That must have been when California's last drought ended, a key piece of information for understanding the region's climate cycles. Carbon-14 has helped open up deep insights into the past, but it's just one of hundreds of radioactive isotopes, that is, elements that decay. In fact, at the bottom of the periodic table, beginning with number 84, polonium, all of the elements and their isotopes are radioactive, including the element that stands for both the promise and the peril of radioactivity, uranium. 92 protons, 92 electrons, and 146 neutrons. Before the nuclear age, uranium was thought to be the end of the periodic table. But in the last 70 years...
Alright, so that takes care of that. So let's fill in a couple pieces of information in our note sheet here. So just a quick animation here for you guys about half-life. Let's say we have some sample of some element, and the red circles have a 5-second half-life, and there's 16 of them right now. So after 5 seconds, how many should be left? Well, let's see. Okay, obviously 8 are left. The green circles are obviously not the same identity anymore, so we have 8 left. So after another half-life, which is 5 seconds, we should have half of the amount left. So it's not 0, because we have to go off of what half of 8 is now. So half of 8 is obviously 4. So after 5 seconds, we should have 4 left. So let's make sure. Okay. So we have 4 left. That was another 5 seconds. So 10 seconds have passed. Another 5 seconds, and we should have 2 left. Alright. Now, after another 5 seconds, we should have 1 left, and then not 0, but after 1, half of 1 is a half, and then 0.25, and then keep going from there. Obviously, until you get down to a very, very small number. So you never really reach 0, because you're always taking half of what you have left. Okay, 1, and then we keep going from there. Okay, so each isotope has a characteristic half-life. You can see that here. So some are really long. Carbon-14 is 5,730 years. Uranium-235 is 7 times 10 to the 8th years. So it's a relatively stable, unstable isotope, right? Because it still does decay, it just takes a really long time. Some take, microseconds to decay and are very unstable. Okay, so the longer the half-life is, the more stable the isotope is. And half-lives are constant, and they can't be changed by the sample size, temperature, or pressure. I talk about that a little bit in AP Chem when we talk about half-life in our kinetics unit. It's a very small portion of it. But just like the slide that we just saw, the half-life was 5 seconds. So it didn't matter if we started with 16 pieces in our sample or 32 or a million. It would take 5 seconds for half of them to decay. That half-life time is consistent. So we can use this for carbon dating, as we saw in that video. Radioactive waste is really interesting because with our nuclear fission, our power plants, once the sample of uranium has been has decayed, what do we do with the radioactive waste that's left over? It might not be more stable or safe for hundreds or thousands of years. So where do we put that? It's a really interesting thing to talk about. So very quickly here, how do we do these half-life problems? I'm going to try to do this. I apologize for all the clicking that you're going to hear, and if there's any lag with my mouse, but we'll do our best. So strontium half-life, strontium-90 has a half-life of 28.8 years. You start with 10 grams of that. So we're going to start with 10 grams. You can make fun of my handwriting later. At t equals 0, so that's our initial time. How much strontium-90 will be left after 86.4 years? So we know, oh my goodness, we know after 28.8 years, we're going to have 5 grams of strontium-90 left, because the half-life is 28.8 years. So we have 28.8 years. Sorry. Okay. So I want to know how much is left after 86.4 years. So I'm going to go through another half-life. So after another 28.8 years, we're going to have 2.5 grams left. Okay, so that took 28.8 years. Well, we haven't, added up to 86.4 years yet, so we're going to go again. So after 2.5, we have half of that, which is 1.25 grams. That took another 28.8 years. So have we let this sample sit for 86.4 years yet? Well, if we add all of those up, we do get 86.4 years. How much strontium will be left? We have 1.25 grams left after 86.4 years. Okay, simple as that. They get a little bit more difficult, which is the next one in your packet. So we'll take a look at that one. I guess we'll do it here. Actually, I lied. Let's do it here so we have room. So for the next one, it's a little bit different because you have a sample of radon-222 and it tells you the half-life is 3.8 days. The sample was not tested until 11.4 days after it was collected, at which point it contains 6.5 micrograms. 6.5 micrograms, that's micro. How much did the sample contain when it was collected? For this, we have to go back in time. Okay, so let's go back in time, one half-life. So we're going back in time. So if we go back in time, there's going to be twice the amount of radon there. So if we go back in time, 6.5 times 2 gives you 13 micrograms. Okay, we went back in time 3.8 days. 3.8 days. My timer's running out here, so I'm gonna hustle through this. If I go back in time another 3.8 days, I have twice as much radon there. So that would be 26. Okay? Well, I want to go back in time 11.4 days. So I'm going to go back in time another 11.4 or another 3.8 days to get to 11.4, and I'm going to have twice or double 26, which is going to be 52 if my mental math is correct at this early time in the morning here. Okay, so that's another 3.8 days. Okay, so we went back in time 3.8 days, 3.8 days, another 3.8 days. So we went back in time a total of 11.4 days here, if you add all that up, and we have 52 micrograms, what we started with. So it's not a big deal here. You're either letting the sample decay, or you're seeing how much you have at some point in time, and I want to know how much I initially had. So I'm doubling everything to go back in time. Okay, so I have a minute left in the recording here before it cuts me off on the free version that I'm using. So if you guys go to the next page in your packet, there's just some practice half-life problems. You guys can work through those. I haven't quite figured out how we're going to check homework yet with all this going on. So complete that, and I'll be in touch about how I'm going to check that. I might have you put it, take a picture and put it in a Google Doc or something. We'll kind of see how it goes. Anyway, that's the lesson for today. So you guys have the rest of the time in class here to work on those problems. They won't take you long at all. Answer key will be posted in the answer key folder at some point in time, so you can check those. And I hope this made sense to you guys and found it kind of interesting about how we measure the stability of some of these radioactive components. All right? All right, guys. Thanks a lot. Talk to you later.